Hello students, in this video I will tell you about the direct comparison test for infinite series. What this test will allow you to do for certain series is to conclude that the series you're interested in either converges or diverges by comparing it to another series whose behavior you already understand. Now what the test says is that first there's an assumption here. Assume that eventually you have 0 less than the terms an in one series here, and those terms are less than the terms bn in another series here. So you have two series, and eventually those terms are non-negative. That's why there's the 0 over here. And also the terms in the second series, bn, second over here, obviously I've written it first here, but the terms in the second series, bn, are going to be bigger, or at least as big as the terms in the first series here. So if that's true, then you can conclude that if the bigger series converges, see bigger because the terms here are bigger, if the bigger series converges, then the smaller series converges. That makes sense? And then you can also conclude that if the smaller series, see this one is smaller than that one, if the smaller series diverges, then the bigger series also diverges. Now this has a little bit of subtlety in it, so let me draw some pictures to illustrate this. So first of all, there's this word eventually in here. What does that mean? So let me draw some integer tick marks on this graph. So I'm going to have n going this way. And then I'm going to use open circles to stand for the an and closed circles to stand for the bn. So here's, I guess I started the index down at 0, so I will start the index at 0 here. And this will take me a second to draw. See, this here is A0, this is B0. Now you might complain and say, well, here the A0 is bigger than the B0, and over here I said that the B's are bigger. And that's exactly the point. I said eventually the B's are bigger. So that's why I'm drawing this where it doesn't necessarily do that at first. Okay, so here's an example of this kind of situation. So here's A1 and B1. Here's A2. Let me mark all the A's first just so I get it correct. A5, A6, A7, A8. Hopefully this is legible on the video. And then B1, B2, B3, B4. Where did I goof? I missed a B3 here. So this here is B3, B4, B5, B6, B7, B8. So you notice that what's happening is eventually, and by eventually here I could draw a line here. And so ignore all this that happens in the first few terms. Eventually what's happening is that the terms are positive in both cases, or at least they're non-negative. Both an and bn are bigger than or equal to 0 here, and the b's are bigger. Now, in this case, if you have something that looks like this general picture, that's when you can use these tests. If the bigger one here converges, then the smaller one will converge. If the smaller one diverges, then the bigger one will diverge. And this makes sense because if the bigger one converges, and that means you get a finite number essentially by adding up all these infinite terms. Well, then if you add up a bunch of smaller numbers, you should expect to get a finite number too. So that makes sense. And then also the other way, this makes sense as well. If when you add up all these smaller numbers here, you get an infinite value, it diverges to infinity, then obviously the bigger ones, if you're adding up bigger numbers, that will diverge to infinity as well. So the test makes sense. It's something you should expect it to behave this way. Now, what can you use this test for? Well, that's what I've just been explaining, really. Series with positive terms, oftentimes this word positive is used to really mean non-negative. So it includes the possibility that some of the terms are zero. That wouldn't make any difference. So that's what it really means in this context. It really means non-negative. And that just has to be true eventually. Now, sometimes calculus books, what they'll do is they'll say this eventually. They'll say there exists, and then they'll have some big number m, such that if the index here n is bigger than that big number, then this will be true, that the terms are both non-negative and that the b's are bigger. That's just a more sophisticated way to say it. I think the word eventually captures the necessary meaning for us here. Let's look at a few examples of using or attempting to use these comparison tests. So the first example I have here involves 1 over n cubed and 1 over n squared. So here I have an is 1 over n cubed, bn is 1 over n squared. Now I know that this one, 1 over n squared, converges, and I know what it converges to. I actually know it converges to pi squared over 6. Now you could tell that this converges in other ways, using other tests, the integral test or the special case of the integral test, which is called the p-test. There's other ways you could conclude that this converges, but we're just going to assume that we know that it converges. Now, for positive integers, n squared is smaller than n cubed, so 1 over n squared is bigger than 1 over n cubed. So you're in exactly this situation here, where the bn's are bigger, these are bigger. You think of these that are shrinking faster because, what do those terms look like? You've got the an terms are going 1 over 1, 1 over 8, 1 over 27, and so on. And so these are all going to be smaller or equal than the b terms, which is 1 over 1, 1 over 4, 1 over 9, and so on. So that satisfies the hypotheses, and so we can compare these series. And so the conclusion is that this one converges. Now, of course, this test tells us nothing about what this converges to, except since it has positive terms, it has to be something bigger than 0. And since this series is bigger, it has to be something smaller than pi squared over 6, but that's all it tells us. It does tell us it converges, though, and then we can proceed to estimate numerically what the answer is. So let's look at the next example. So here I'm going to compare the harmonic series to something that has a square root in it. So this will be n equals 1. Let me move this over so I have room to write my an and bn there. So we have n equals 1 to infinity 1 over n. N equals 1 to infinity 1 over the square root of n. So here, an is 1 over n, bn is 1 over the square root of n. And notice this is in the same position as what we were before. The n grows faster than the square root does. So that means that 1 over n is going to be smaller than what the 1 over square root of n is. And they're both positive. So an is sandwiched between 0 and bn here. Now in this case, what we know, we're familiar with the harmonic series. So we know that this one diverges to infinity. And so the conclusion is that this one also diverges to infinity. It's bigger than something that diverges, and so it also diverges. All right, and so let's look at one more example. Now this is one where I've taken the harmonic series, but I've put a negative sign in there. And then I'm comparing it to our familiar inverse squares series. So here an is equal to minus 1 over n. bn is equal to 1 over n squared. Now in this case it's true that an is less than or equal to bn for all n, and that the second series converges. The bigger one, if you like, because, bigger in the sense that the bn's are to the right on the number line of where the an's are. So this one converges, but this one diverges. So what went wrong? Well, the series don't have positive terms in this case. There's a negative sign here. Now, why does this diverge? Well, it diverges for the same reason that the harmonic series diverges. All it is the harmonic series with a negative sign in front of it. So the harmonic series diverges to infinity, this diverges to negative infinity. It behaves the same way. Now, of course, what this looks like, I'll have to erase this in order to draw it. But what this looks like is you've got, in this case that didn't work, what you've got here is you've got the, let's see, I do the ANs, the smaller ones with open circles. So I'll do that here. So this was a minus 1, minus 1/2, minus 1/3, minus 1/4, and so on. So this is, so this here, in this case, this was well, I guess it doesn't start at 0, does it? That's because it's a harmonic series. Let me do this over. That will be enough. And so this here is a, that's supposed to be not a 0, that's supposed to be a dot. So this is A1 equals 1. This is going to be A2 equals 1/2. I mean -1, I'm sorry. -1, -1/2, and so on. There's not really room to write the others, and it doesn't matter. The point is just that we're showing so this here, what this is this is the negative harmonic series. So that's the one, this one here. And then what I've got for the b's, this is b1 is 1/1, which I'll just call it 1 like I did there. So b1 is 1, and then b2 is 1/4, and then b3 is going to be 1/9, and so this is getting very close to the axis here. And so what you've got is, yes, you've got, so this is the picture of the series, or the terms of the series 1/n². So yes, you've got the b is bigger. So so you see in this picture, the b there is bigger than what the a is. But what you don't have is it's not trapped. See, you need a lower bound too, essentially. That's what it comes down to. You need a 0 there to trap this other series between something that you know converges and something else that you know converges, 0 in this case, and you don't have it. Instead, it's below down here. And so, I mean, you could think about it, you could do the same sort of logic if I had these points were like way down here. Obviously, these are a bunch of large negative numbers. It's going to diverge to negative infinity. It still satisfies this part of it, that the bn is greater than the an. But the point of all this is that you can't just naively compare series and say, okay, the big one converges, so the little one will converge. You have to know that the terms are positive, or at least that they're eventually positive, so that the little one isn't really large and negative. Just because it's to the left on the number line doesn't mean the terms are really small in magnitude. So anyway, hopefully this gives you an idea of when you can use direct comparison tests.